morning, everyone. Today you're going to continue induction machines as an extension of lecture 16. In that lecture, we covered the basic principle of operation of induction machines. We defined some important topics there, such as the slip, the frequency in the rotor and the stator. And in this lecture, we're going to use those principles to develop an equivalent circuit that will allow us to estimate torque and speed in an induction machine. You will see that this will become very similar to the circuit we use to describe a transformer, hence the need to cover a transformer in one of the early lectures. The induction machine will operate exactly like a transformer. We'll then see how we can expand the equations to develop equations for torque and speed, and see how we can improve the starting torque in induction machine, which is typically lower than the nominal torque. So by the end of this lecture, you should be able to model an induction machine, find an equivalent circuit model for the induction machine, and estimate the torque and the speed of an induction machine. Induction motors, as we covered in the last lecture, have many applications. Here is one of them. This is the FORCE maglev, is a magnetic levitation train that was opened in 1984. And this maglev stayed in operation until, I think, 1995. It uses a system that creates a magnetic field between the rail and the train, the tracks and the train, and that makes the train levitate. And there's another system then that is used to propulse the train along the tracks. In 1995, this train was taken out of service and was replaced with a cable-driven system. The reason, I don't know, but it was the first implementation of a maglev train. There are some in operation today. I believe there's one in China, but this one is the first one. Here's another example of an induction system that we see in trains. This is a train that still operates, and it uses aluminum between the space along the tracks and coils that will create an induction in the aluminum. That induction creates a magnetic field, and that is used to propulse the train along the tracks. This is still in operation. It operates in the exact same principle of an induction machine, except that this is a linear motor as opposed to a rotating machine that we covered before. So this type of motors, they can be used from small appliances to trains. They are very versatile. And the reason, again, is, as we discussed before, the construction of this machine is relatively simple. It doesn't require the use of permanent magnets. It simply requires the use of an alternating magnetic field and a closed path for a conductor to experience an induction in the said magnetic field. One question that we're going to answer today is, how can we estimate now the torque developed by these machines, either in a linear system or any rotating system? How can we estimate the torque, and how is the torque related to the speed? We had a clear relation between torque and speed in a DC motor. Let's see how that is in an induction machine. So before you go any further, let's go back to lecture 16 and do a quick review of the operating principle of an induction machine. We have two principles to cover. The first one is Faraday's law, which states that if a conductor is moving in a magnetic field, or if a conductor experiences a changing magnetic field, a magnetomotive force will be applied or develop in that conductor. And if you close the path of that conductor, we create a closed path, then that EMF will induce, that MMF will induce a current in the conductor. And that intensity of that voltage is proportional to the intensity of the magnetic field, the speed at which the conductor moves, and of course the length of that conductor. That's principle one. Now if you close the loop, you get a current. And then you have Lenz's law explaining that if there is a current, the current is in a magnetic field, that current will experience a force. And that force is also given as a function of the intensity of the magnetic field, the length of that conductor, but now it also depends on the magnitude of the current that conductor is passing. This now creates a force. And this force, if we do a certain arrangement in a induction machine, that force now develops a torque. Okay, and the torque is now the result of the interaction between the field generated by the current that passes through the coil. It creates its own magnetic field. It interacts with the magnetic field from the environment, and the result is a force. As you saw in the past lecture, if the conductor is moving, or if, let's put it this way, if the magnetic field is moving along the conductor, the force experienced by that conductor will follow the direction of motion of the magnetic field, which is the exact principle we use to develop an induction machine. And the idea here is very simple. We have a path for this conductor to develop a current. That's what we call the rotor. So the rotor has its own winding, has turns of wires like that, develop or arrange in slots along the rotor. And our job now is to create an alternating magnetic field. Well, I shouldn't say an alternating magnetic field. We should create a rotating magnetic field. If we create a rotating magnetic field, let's hypothetically call that magnetic field B and give this direction. If this magnetic field rotates, then each conductor in the rotor now experiences a force that will make the rotor rotate in the same direction as that of the magnetic field. The question then becomes, how do we create this rotating magnetic field? Well, the idea is simple. We have three phases, three coils. Each coil is connected to a phase. Each coil has, or each phase, I would say, has two coils that are connected in series like that. So this would be a two-pole machine. We have coil A here, coil B there, and coil C right there. And now we take these three coils and we give them a alternating current at a given frequency. What happens? Well, if we have these three coils and an alternating current, if we arrange the coils in a specific pattern and we phase shift all these currents exactly by the same amount to match the mechanical configuration, then the result is a magnetic field that has a given intensity, a fixed intensity, but it now changes orientation. The resultant magnetic field now changes orientation. So these three phases are connected, let's say, in a delta configuration like this. And we can say that when phase A is activated, let's say, it creates as an axis like that, and it will create an EMF that points that way. When you do phase B, let's say, would be this axis here, would create this magnitude, and phase C as well. We can now add them up, and this would be the resultant magnetic field vector B for that specific combination of phase A and phase B intensities. These intensities will take them from this graph, which shows the current applied to each of the coils, and you can see here that they are shifted in time by the same amount, in this case 120 degrees. We can now probe this signal at any specific point in time, let's say at point t0 here and there. We know the intensity of the current for each coil. We can now plot the resulting vectors for each coil, and you see that the resulting vector as a sum of the EMF generated by each of these currents will now point to the right. We can move on to point T1, let's say, and do the same. Now take the intensity of each current, put that on the plot, on the graph, and create the resulting magnetic field. And we see now that the magnetic field rotated by 45 degrees. So because this is a two-pole machine, it has three phases, it is very likely that the shift between T0 and T1 is also 45 degrees, electrically. Mechanically, we see now the resulting vector is also shifted by 45 degrees. And you can continue this process on and on. We can go to another point T2 right here, and you see that at T2 current IA is 0. We have current IB and IC that have the same value but opposite signs. We plot them here, and we shall see that the resulting vector would be upwards. right? So we can conclude that as we move along this point, this curve, as we move along time there, this vector keeps the same intensity, but it now rotates around the core. To rotate around the core, will rotate at a given speed, and that speed will depend on two factors. It will depend on the frequency of these currents, of course, and it will also depend on how many poles we have in the machine. The more poles we have, the slower the magnetic field rotates. Okay, so nothing new here. This is from lecture 16. Once we now have this alternating magnetic field, conductors in this closed loop path, or in the conductor that is subjected to this alternating magnetic field, for this rotating magnetic field, will experience a torque in the same direction as the alternating magnetic field. What else did we discuss last week? Another important consideration is that the rotor will rotate, but the rotor rotates at a lower speed as that of the magnetic field, than that of the magnetic field. And why is that? Remember again that it rotates at a lower speed because the rotor needs to experience a changing magnetic field. If the rotor moves with the magnetic field in synchrony, then from the rotor's perspective, there is no changing magnetic field, and the induced EMF in the rotor is zero. So in order for work to work, we need the rotor to rotate at a slightly lower speed than that of the magnetic field itself. Okay, that's the principle of operation, and we call that a difference. We call the slip of the DC, the induction machine, which is a number between 0 and 1 when it operates as a motor. Now let's go one step ahead. Now we know how that works, and develop a equivalent circuit model for the induction machine. We can start by looking at the simple arrangement here, where we have three coils that are the input to the system. They're connected to a neutral point, and this would correspond to these three wires going in here. Well, nothing new there. And then we have these three coils in the stator. We have an air gap between the stator and the rotor, and in the rotor we have another set of coils, here represented as three coils as well. And these three coils are connected, are short-circuited to themselves like that. Right. As you're going to see later, sometimes it is desirable to have access to the terminals here. So we may open these terminals, connect them to rings like that, so that we have external access to them, and we can connect them if needed. We can add a resistance between them if needed. So this would be the slip rings that we see here. We'll see that they have some certain use later, but in general, this part here would be the rotor equivalent circuit. So now we're going to do an analysis one phase at a time. Let's determine or establish the terminology we are going to use. For the stator, we have all the variables here: the terminal voltage, the winding resistance, the winding inductance, the induced MMF, the magnetizing inductance, and the core loss resistance. So all the indexes 1 will now refer to the stator, and for the rotor, we'll use numbers 2. Okay. And you recognize this terminology from the transformers. It is exactly the same circuit as you're going to see later. So now let's start by modeling the rotor. Let's start with the stator. You're going to see an equivalent circuit from the stator like that. Actually, before we go into that, let's just also look at how the power flows in this system. So we have the power going in, the electrical power going in. If the system operates as a transformer, then you know that you have core losses and eddy current losses. Right? This leakage flux in a transformer that represented the flux that it doesn't circle, that doesn't loop in the ferromagnetic path. It is the same here. In fact, it's more significant in the case of an induction machine, because now there is an air gap between one coil, the primary and the secondary, there is a large air gap. So there is a significant core losses in the leakage inductance in this example. Eddy current loss, of course, we have a ferromagnetic path somewhere, there is going to be some eddy current losses. So from the total power that we put in, some is dissipated in the stator and some then makes it to the air gap. And you're going to call that the power in the air gap. We're just going to call that a P. From that power that goes in the air gap, some of that power is dissipated in the rotor in the same way that you have that in the stator. Is dissipated in the rotor, yeah, exactly in the stator, in the rotor, as we have that in the stator, and as eddy current loss, and some of that is then converted into mechanical power. From that mechanical power, we have an output power, but there is some losses between the developed mechanical power and the output power due to friction, mechanical friction in the shaft. Okay, so from the portion of energy we put in, the rotor, the stator itself dissipates some of that, some makes it to the air gap, then more energy is dissipated in the rotor, some of that goes is effectively converted into mechanical power, some of that mechanical power is dissipated in friction, and then some of that eventually gets out as useful mechanical power for the system. So now that we have this analysis, let's see what happens at the stator side of the motor. So here is the stator equivalent circuit. I think this rings a bell. This is exactly the same model we had for the transformer. There's no difference. So let's review this as it was a while ago. So we have the input voltage to one phase. This is one phase of the motor. We have the winding resistance here represented as R1. We have the leakage inductance, which represents the magnetic flux that it doesn't loop in the core. That is, does not converted effectively into magnetic flux or MMF in the rotor on the other side of the transformer. And we have the eddy current loss represented here by this resistance in the core, and we have Xm, which is the magnetizing inductance in the core. We have a current going in. Part of the current magnetizes the core, and part of that dissipates power in the form of eddy current, and the one that actually goes to the secondary will now create a MMF E1. In this example here, or in the transformers, I would say the magnetizing inductance was very small, and we could neglect that. In an induction machine, the magnetizing current is much greater than that we saw in a transformer. Why is that the case? The magnetizing current is much greater than the magnetized current in a transformer. Why? Any ideas? Because of the inductance. The inductance, which inductance? This inductance or that inductance? Because of Xm. Yeah, we are getting there. We're getting there. What does that inductance represent? It represents the magnetizing inductance. And because in this system we have an air gap between the primary and the secondary, it will take a significant amount of power to magnetize the air gap. As we saw before, for materials that have a very high permeability, well, it's not very hard to magnetize them. But now we are dealing with air. We need to magnetize the air gap. And if we need to magnetize the air gap, this current will need to be significantly higher than in a transformer. And yes, it is, because then, as a result, this inductance here will be much greater than that we saw in a transformer, or this reactance will be much greater than we saw in a transformer, because now need to magnetize the air gap. This entire system, if we apply a frequency F1 from the input voltage, then the entire system runs at a frequency F1. We'll see that the leakage reactance and the magnetizing reactance here, they are both operating at the input frequency. Okay, so nothing really new here. It's a transformer. The only difference is that now this magnetizing inductance is actually due to the air gap between the coil, the primary coil and the secondary coil, and this reactance, the leakage flux, is also greater because you don't have a very established, a clear ferromagnetic path for the magnetic flux.
Sorry, just clarification.
Yeah.
Uh, the primary coils are the ones in the stator, and the secondary ones are the ones in the rotor.
Yes.
Okay.
We apply a
Um,
voltage to the stator. Right. So
the
this is
alternate
the circuit.
voltage.
Yes. This is one phase, and then the stator magnetizes the core, which magnetizes the rotor, and the rotor is the secondary.
And you said the magnetizing energy is much higher here because of the air gap.
Yes.
When designing induction motors, then, like, would I, if I just increase the number of coils in the stator, would that sort of decrease the air gap because there's just
Yeah.
less of an air gap for the rotor to rotate to hit the next coil?
Yes. That's a very good point. You put as many coils as you can to make a more uniform magnetic field and minimize the need to magnetize a large area. So you will see in an induction machine, the ones that I've been using here, they have three coils, but you can have one phase can have multiple coils distributed
Oh,
um,
okay.
in space, right?
Thank you.
So that's for the stator. Now let's move on to the rotor. So from the rotor, we'll treat this rotor as a load, as in the same way you did for the transformer before. We have the same here. We have a magnetizing, or sorry, we have a leakage reactance, and we have the winding resistance of the rotor right there, R2. Now, something to consider here is that if the EMF in the first case at the output of the transformer was E1, that E1 was at the input frequency. At the rotor side, we know that if there is anything induced here, it will be induced at the slip frequency, at the slip S, that we defined as Ns minus N divided by Ns, the relative difference in speed between the stator and the rotor. This is the frequency that the rotor sees the change in magnetic field. So it is understandable that this voltage here will be induced at that specific frequency, that is S times F. So everything here will run at a frequency S times F1. Everything runs at this frequency. What do you have in this rotor circuit? Well, we have these two reactances. We have the reactance and the resistance, and we have a input voltage here, or the resulting MMF, that is S times E2. E2, if you remember from the last lecture, is the voltage that is developed in the rotor at standstill. And as the rotor starts to rotate, then that voltage decreases, and it goes to a value of S times E2. That's from lecture 16. So at standstill, we have E2. When the rotor rotates, it will be E2 times S, and that's the exact input here, voltage input to the rotor as compared to the static case. Okay, so that's one thing to note, and the other thing to keep in mind is that this is going to operate at a different frequency than the stator. The stator operates at a frequency F1. The rotor will operate at a frequency S times F1. We can apply Kirchhoff's law to this circuit to find the current I2. And it's relatively simple to do. We have the input voltage divided by the total impedance in the circuit, and this is what we have. E2 times S divided by the resistance plus the reactance. And if you notice here, we have S here and S there. We can divide the whole expression by S, and this is what we see. E2 divided by R2 over S plus JX2. So we can say that the effect of having the rotor rotating at a different frequency is equivalent to having a resistance that now changes depending on the slip frequency of the rotor itself. So this equation gives us this circuit gives us that equation. We divide everything by S. We have an equivalent circuit there that we can now represent here. See now that the input becomes operates at the frequency of the rotor, the stator itself. The stator and the rotor now operate at the same frequency. The only difference is that we have this term R2 over S, which indicates that we can see the rotor as having a resistance that depends on the slip factor. Any questions here? Any questions about going from one circuit to another? No? So again, Kirchhoff's law, we get the current. We see that the current establishes a voltage in the rotor frequency. The reactance is in the rotor frequency. But now if we divide everything by S, we have E2, same as the stator frequency. We have X2 stator frequency, but now we have a resistance that depends on the slip frequency or the slip factor, which is a big advantage compared to the first configuration, because now everything operates as in the rotor, in the stator frequency. So we can now combine these two parts of the transformer. So let's do that. Here we have it. We had the first one that ended here in the stator, and now we have the rotor added to it. This is the rotor. What can we see here? Well, it's really just combining them, but we notice that if you combine them, there is a number of turns. There is a turn ratio between the rotor and the stator. They may not necessarily have the same number of turns. So the turn ratio A needs to be taken into account, and you remember the impedance transfer in a transformer. If you take the impedance from the secondary and move that to the primary, we need to multiply that by the square of the number of turn ratio, which in this case is A, as we use for the transformer. So this is just to say that X2 now becomes X2 prime, or the referred secondary impedance in the primary. R2 is the referred resistance of the rotor in the primary. All right. And that again is multiplied by A squared. So R2 prime equals to R2 times A squared, where A squared is the turn ratio N1 divided by N2. Right. And same now applies with the EMF. The EMF on one side equals A, the number of turns, times the EMF on the other side. And that's the only thing we need to consider here before we merge these two circuits together. But here it is. Okay. And once again, if you look at the stator and the rotor, we are just combining the two circuits. The only consideration is to properly transfer the impedance and transfer the voltage and current from the secondary to the primary. What is the power in the rotor? Well, the power in the rotor, if you just think of a motor as standstill, the power in the rotor would be simply, let's call that P2. It would be I2 squared times R2. If the rotor is at a standstill, we have R2 divided by S, but at standstill, S equals to 1. How did you define S? S equals to the synchronous speed minus the rotor speed divided by the synchronous speed. At standstill, this is 0, S equals to 1. So when the rotor does not rotate, S equals to 1, the power that it goes to the rotor, the power that crosses the air gap, is entirely dissipated in the form of copper loss in the rotor. Because this would be again divided by S, S equals to 1. Now, if the rotor starts to rotate, R becomes R2 over S. And this is now the power crossing the air gap. Crossing the air gap is R2 times I2 squared divided by S, or the power that crosses the air gap is simply P2 over S. Right? P2 is the standstill power, or the power dissipated in the winding of the rotor. And when you divide that by S, that S, again, here represents the change in the reluctance, the changing in the resistance as the rotor rotates. Okay. So we have a power crossing into the air gap. Part of that now dissipates in the form of Joule losses, as in P2, and part of that now creates a mechanical power. So let's see if we can determine what that power is. All right, so if we neglect all core losses, so these will go away, the power input to the motor per phase is simply the current that we give to the motor squared multiplied by all resistances. So you have two resistances that are dissipating energy. We have R1 and you have R2 prime over S. So this resistance and that resistance, and you are neglecting that one. That goes to 0. That's the input power to the rotor, to the motor. What has now been dissipated in the winding? Well, what is dissipated in the winding is a very similar expression, but what you're dissipating is I1 times R1 squared times I1 plus I1 squared times R2 prime. Remember that this represents the power dissipated in the motor when it does not rotate, right? The winding, the copper loss in the rotor. But here we have the total power, and that is divided by S, because part of that is what creates the mechanical power. So the power in accounts for the motor rotation. The loss does not. It's simply the sum of all resistances times the square of the current passing through them. What is the net power? Well, there is a difference between them. We can see that a P in and PW, the dissipated and the input power are different. Where is that going? Well, the difference is being converted into mechanical power. So to find the mechanical power, we can simply subtract them. We know that the power in equals to the loss plus the mechanical power. We can now solve for the mechanical power by subtracting the dissipated energy or the dissipated power from the input power. So here we have the input power. Here we have the dissipated power. And if you solve for the equations there, this is what you get. This is the actual part of the useful part of the power that is transformed into mechanical power. Okay, so let's recap what happened to the energy flow. We had a power going in the air gap. The power going in the air gap was I2 R2 over S, R2 squared, R2 prime. This is the power going into the air gap. That is going to split into two. One part of this power is dissipated in copper loss, and that amount is I2 squared times R2 prime. So we basically multiply the input power in the air gap by S, and then you get the copper loss here. What happens to the rest of that power? Well, the rest of that power, if you multiply the input power to the air gap by S, we get the core loss. If you now multiply this by 1 minus S, or the rest of that power, that needs to be converted into mechanical power. So this gives I2 squared R2 prime divided by S times 1 minus S. And this is exactly what we got there. All right, so we multiply that by S to get the power loss. So the other 1 minus S needs to go somewhere else. So that is actually the mechanical power. So I2 squared times R2 prime divided by S times 1 minus S, that's the mechanical power transferred to the motor that actually creates mechanical motion. Any questions here? Any questions with about these two different powers? So we have power crossing. We have three different powers. Power going into the air gap, that's P. We have power dissipated in the core, that's P2 given by that. What is the difference? P2 equals to P times S. And we have the mechanical power P, let's call that a P, how do they call that? PM, which is the air gap power times 1 minus S. If we add them up, they go back to the air gap power. Okay, any questions?
Is the power from the previous page what we would have represented as P in or P air gap on a few slides ago?
This one? No. Sorry, which slide exactly is that?
The one labeled power flow.
Oh.
With the diagram.
Yeah, so here, this one, right?
Yeah.
So this is the power input to the motor. Then this is the power we are dealing with right now. This is the actual power that goes into the air gap.
Okay.
All right, so some of that power goes in core losses, that's multiplied by S. And some of that now is transferred to mechanical power, that's the one multiplied by 1 minus S.
Okay.
Okay. Any other questions? No? All right. So if that is the case, then here we have the power for that is converted into mechanical power, and you can express this power as a function of the other two powers we had. Let me recap them here. P2 is the power at standstill, I2 squared R2 prime, and P equals to that divided by S, which means P equals to P2 over S. So the first one is the core loss, the second one is the air gap, and the third one is the same as the air gap. Okay, so we can represent the total power converted into mechanical power as a function of these ones as well. We know that this whole thing here is P, so you can rewrite the expression like that. And if we divide the entire expression by S, we can also do P2, and just different ways to express the same information. But this is to say that we now establish two components of this power. One component that is dissipated in this resistance, the other component that now depends on the slip-dependent resistance, and that's the one that is converted into mechanical power. This is the same circuit. If you add these two together, we have R2 prime plus R2 prime over S, S1 minus S. If we expand this, what do we get? R2 prime plus R2 prime over S minus R2 prime. This cancels that, and you are left with the same term we had before. All right. So this is the same circuit, but you are now splitting the load into two components just to represent the power loss and the actual power converted into mechanical power. So if you add these two impedances, we go back to the same circuit, just to re-emphasize the idea. Okay, so let's look at the total mechanical power now. The total mechanical power, that's the power for one phase. The total mechanical power is 3 times that. We can express the mechanical power in two ways. We see here the rotor resistance and the rotor current. Or you can now take the rotor resistance, transfer that to the primary circuit. Now we are dealing with R2 prime, and now we are dealing with I1, the stator current, instead of the rotor current. The same way we could do for a transformer. So express everything on one side of the transformer, the rotor, that was the first equation, express everything in the stator side, that would be the second equation. What is the power? Well, the power is defined as the torque on the mechanical side times the speed. So we can now calculate the torque by simply dividing the power here by the speed of the motor, not the synchronous speed, the actual speed of the motor. This speed is in radians per second, and this is the speed of the motor. From the equation we had before, that the slip frequency, the slip factor was synchronous frequency minus the motor frequency divided by the synchronous speed minus the motor speed divided by the synchronous speed. We can do the same. We can isolate for n, and n would be, if you do the calculations here, would be the synchronous times 1 minus s. This is in RPM as we defined before. So if you want to convert this into radians per second, you just need to multiply this by 2 pi over 60. So you can now deal with the angular velocity in radians per second, which is the angular velocity of the magnetic field, or the synchronous angular velocity, times 1 minus s. That's the actual speed of the motor. If you relate that to the RPM, synchronous speed, it's simply that multiplied by the constant 2 pi over 60. Okay, so this has an advantage, because now instead of expressing our system as a function of its actual speed, we can express that as a function of the synchronous speed. Just need to multiply it by 1 minus s. So you have two ways to do this calculation. We have the actual speed, or we have the actual the synchronous speed, which is the speed times 1 over s. By doing that, we can simply replace the denominator here with s and 1 minus s. So this will cancel that, and you have now the expression for the output torque as a function of the synchronous speed in radians per second. So that's the torque per phase. Once again, it's 1 over the synchronous speed in radians per second times I2 squares. This should be I2 prime, R2 prime. If we go back to the circuit we neglect the winding, the magnetizing inductance, and we neglect also the eddy current loss. We can calculate the magnitude of the current, and I'll replace the no, sorry, this was correct. There's no prime here. I made a mistake because this is I2, right? So if it's I2, is R2. If it's I1, then it would be R2 prime. Okay, so this is correct. Okay, now calculate the magnitude of the current, replace the current in there, and this is now the entire expression for the torque after we do those simplifications. What do you see here? The torque is assumed to be independent of the magnetizing inductance. The torque depends on the speed. That's a very important consideration. The torque depends on the speed, and the torque depends on the slip factor. The torque depends on the slip factor. Okay, so this equation will only hold, of course, when the slip factor is not 0. If they rotate at the same speed, then this equation doesn't hold. Okay, that is the torque as a function of the current in the rotor. And we can now just, here we have a simple plot showing the speed, the torque developed in the motor for different voltages as the frequency, or as the slip frequency changes. Another thing to notice here is that it depends on this, the torque depends on the square of the input voltage. That's very important. It's not linear anymore, as in the case of DC motor. This now depends on the square of it. What can we see here? We can see that the maximum torque will occur at a given point. That depends on the slip factor. What else? The voltage decreases, the torque decreases. And what else can we tell? We tell here that when the slip factor tends to 0, now the rotor produces no torque, and then as that increases, the torque is likely decreases. So this is the torque for one phase. If you multiply this by 3, because you have 3 phases, then we get the total torque developed in the motor. Now let's take this calculation one step ahead, and let's see where the maximum torque occurs. If we neglect the winding resistances, that is these two terms here, let's put that to 0 for simplicity, we can reformulate the torque as shown. We see that the torque now depends on the slip factor. We can now determine the slip that gives the maximum torque. How do we find that? Well, if you want to determine the maximum of this function as a function of s, just take the partial derivative of that function as a function of s, set that to 0, and solve for s. When you solve for s, we'll find the value of s that maximizes that function. That's what equation 12 does. Take the derivative of the torque with respect to s, set that to 0, and find the value of s that will now give the maximum torque, and you call that Sm, the maximum slip for the torque, the slip for the maximum torque. Once you have that value, simply take Sm and put that back into s here to find what the actual torque is. So take the derivative of the function with respect to the variable of interest, set that to 0. Solve for the variable of interest, that gives you at which point we get the maximum of that function. Now evaluate the function at that point, and that gives you the value of the function itself, the maximum value that we are looking for. So two important pieces of information here. The first one is that the total torque will occur at this specific slip factor. And this slip factor can be now controlled based on the resistance of the winding in the rotor. Depending on the winding resistance, the maximum torque occurs at a different speeds. Because the maximum torque depends on the slip factor, if we change the slip factor somehow, we are basically changing the speed at which the maximum torque occurs. So if you find a mechanism to change the resistance of the winding in the rotor, we just found a way to determine at which speed the maximum torque will occur. Right. So let's see here. Once again, changing R will change the maximum optimal slip for the torque. If we want, for example, the maximum torque to occur at the beginning, when the motor starts, should we increase or decrease R2 prime? Now, if you want the maximum torque to occur close to when the motor starts, the slip is 1. So if you want now the maximum torque to occur at a slip of 1, just set R2 in a way that Sm tends to 1, which means that the maximum torque will be at start. Right? How can you physically do that? We'll see that later, but that's the idea. We can now control the magnitude or control the point at which this maximum torque occurs if you find a way to control R2 prime. The maximum torque itself is independent of R2, right? The point at which the maximum torque occurs is now controlled by R2, but the magnitude of that maximum torque is independent of R2. So how do we do that now? Well, these motors, because of the reactance, just 1 second, I have to fix my iPad here. There it is. Because we have such a high reactance in the rotor, at the beginning, when you start the motor, the torque will be relatively small because you need the currents to develop in the rotor as well. So how can you fix this problem? Well, we now have, if you have control over the variable R2, we can now shift to the point at which the maximum torque occurs. Let's again consider the case where we want the maximum torque to start to be at the beginning, to be when the rotor is at standstill, when the motor is starting. Because that's a low torque, let's change R2 temporarily to shift the point of maximum torque to a point where Sm equals to 1. The maximum torque will occur at the slip of 1 or close to 1. How do we do that? We need to control R2. So here is where the slip rings will come into play. We can attach each of them to a resistance, and you can increase that resistance in the beginning. When the rotor starts, we attach the rings to this resistance. So now R2 increases, the point of maximum torque shifts towards this slip of 1. And once the rotor starts to rotate, we turn off the resistance and we just short circuit this winding resistances here so that we go back to a normal operating mode. That's one way. It would be a on-off system. Or we can use the idea of duty cycle. We can have now this resistance connected to the secondary winding or to the rotor winding. We have this resistance, and we have some sort of transistor here that now shortens that resistance. When the transistor is on, we have a closed circuit, so current flows like that. And the effective resistance in the winding is simply the resistance R2. And if you modulate this, and when it's completely open, the resistance would be this resistance called that R. And if we now change the duty cycle here, let's say a duty cycle of K, we can now make the effective resistance go from 0 to R. And the effective resistance as a function of the duty cycle is now R times 1 minus K. So by now changing the duty cycle, we change the effective resistance in the rotor winding, which allows us to control the point where the maximum torque occurs. Now, simple solution and quite interesting way to do this. If you want to drive a specific load at a specific speed, you can arrange this duty cycle to give you the exact resistance you need to shift the slip point so that you get the maximum torque at the exact speed the motor is operating at. Or simply attach a resistance when the motor is at start, and once the rotor starts to speed up, then you can shorten that resistance and go back to a normal operating mode. Okay. Any questions here? No? Is it clear how we can control the point of maximum torque through this arrangement? It would be an interesting final exam question. All clear? All good? All right. Very well. Are there any other questions before we do some exercises?
Question?
Yep.
Would you mind explaining the braking portion of the graph?
The braking, yeah. Yeah. This part here. Yeah, so that S is N minus N divided by NS. Right. So for this to be greater than 1, we need N to be smaller than 0. Right? Which means that the rotor and the stator are operating at different directions. One rotates clockwise, the other one rotates counterclockwise. Okay, and the motor operates as a brake. If the speed of the rotor is greater than the synchronous speed, then we have a negative slip. That means that it operates as a generator. Does that make sense?
Yep, thank you.
Yep. Any other questions? No? All right. Okay, my iPad is stuck again. Let me just fix this, and then let's do one exercise. do a few exercises actually. So this is not very complicated. You see that this behaves exactly like a transformer, and that's the beauty of these models. There's really nothing different compared to a transformer. So let's do exercise 79, and let's do another one, another two if you have time. Let me just double check something. Okay, all right. So you have here a 3-phase, 4-pole, 60 hertz, 11 kilowatt, 460 volt, 1728 RPM. Is this the version you have, or are the numbers a bit different? I changed them last night. I'm not sure if I uploaded.
It's the same.
It's the same? Okay, good. The final version. Okay, so that's the characteristics, the whole characteristics of the motor. It has, it's a 11 kilowatt motor. The windage and friction loss of the motor is 750 watts. So we give it input power of 11 kilowatts. There is windage and friction loss at 750 watts. The question is determine the power developed by the motor, the mechanical power, the air gap power, and the rotor copper loss. All right. So let's then do that. Let's summarize here what we have. We have a 11 kilowatt motor, and we have 750 watts in losses. What else is important here? We have a 4-pole, 60 hertz. Question A, what is the mechanical power developed in the motor? What is the mechanical power developed in the motor? Any ideas? What is the mechanical power in the rotor? Remember that the mechanical power is the input power minus all power losses. Okay, which gives the input power is the nominal power 11 kilowatts minus 750. This is 10,250 watts. All right, this is the actual power that is converted into mechanical power according to the power flow we established before. Okay, what is this power? Just to go back to our definition, this power would be what we called R2 prime, R2 times I2 squared divided by S, which would be the air gap power times 1 minus S. This is now the power that is converted into that amount of mechanical power. Okay, easy. Second question is, yes, go ahead.
Is S a constant value, or is it given to us?
What is S? S is NS minus N divided by NS. This lift factor. Synchronous speed, rotary speed, synchronous speed. We're going to, so let's calculate that now that you asked. What is the factor S? What is S? This is the slip factor, again from lecture 16. What is S? We have the synchronous frequency, the motor frequency times NS. What do we have from the problem? The problem says that it actually gives the speed of the rotor, that is 1728 RPM. It rotates at this speed when it delivers this much mechanical power. What is NS? That is the synchronous speed. That's the speed at which the magnetic flux rotates inside the core, inside of the air gap. We have then, that is given by 120 times the frequency divided by the number of poles. This is from lecture 16. So this is 1620 times the frequency, 60 hertz, divided by the number of poles, that is 4, and that is 1800 RPM. Now you can calculate the slip factor. The slip factor is 1800 minus the actual speed, 1728, divided by 1800, which is 0.04. Yeah. Okay. This is the slip factor at this specific operating condition, and this is the power converted into mechanical power. So that's the power that was converted into mechanical power. The question B asks, what is the air gap power? What is the air gap power? Let me just ask you this just to see, this is a simple question. Is this air gap power smaller or greater than this PM?
Smaller.
Smaller. Why is that smaller? In which way? Let's recap in which way the power is flowing. We have a power going in. Then this power going in is dissipated in the core loss, and then part of that goes away. That's what we established here. And then we have power crossing the air gap. Part of this crossing the air gap is dissipated in the rotor. Part of that is converted into mechanical power. So this is the one that are multiplied by S. This is the one that multiplied by 1 minus S. So the power that crosses the air gap is greater than the power developed in the motor, in the mechanical power, because part of this power is dissipated through power losses in the rotor winding. All right, this must be clear. All right, so that should be actually greater. All right, just so that's actually a good mistake to make, because now we can establish again one more time the power flow. So don't worry about that. Okay, so what is the air gap power? How do you relate the air gap power and that?
Is it just PM over 1 minus S?
PM over 1 minus S, exactly. So PM is the power that crosses the air gap times 1 minus S. All right, so the power that crosses the air gap is simply PM over 1 minus S. PM is given here, S is given there. We can replace those values, and this gives 10.697 watts. Mechanical power, power that crosses the air gap. They are different because part of that was dissipated in the rotor copper loss, which is question C. How much energy was dissipated in copper loss in the rotor? That would be P2, I2 squared times R2. And what is P2? Is air gap power times air gap power times what? Let's recap again. See,
S.
from times S. Yeah. Times S. Right? So power in the air gap multiplied by 1 minus S here. This is the air gap power multiplied by 1 minus S gave us the mechanical power. The rest, which is S, is the power dissipated in the winding, which is 427 watts. Right, this P is this P here. And this S is the S there. Which is the difference between these two, basically. Right, that minus that. Okay. Any questions? Good? So are we good with the power flow and all these different powers? P, PM, PS, sorry, P, PM, P2, and how one is 1 times S, one is minus 1 times 1 minus S. Is this all good? Yeah? No? Perhaps? Okay. So that's exercise 79. Let's do one more. Let's do exercise 80. No more questions here? Okay, so now let's do exercise 80. So here, this is a more comprehensive one. We have a 3-phase, 460 volt, 60 hertz 4-pole. One rotor has the parameters shown. The core losses due to RC can be neglected. Calculate the starting current, the starting torque, the full load at no full load slip if rotating at 1740 RPM, full load torque, and the resistance that must be connected in the rotor so that the maximum torque occurs at the start. Okay, so I'll give you a few minutes to think about this. As I erase here the light board, I'll make some room. Think about how to solve the first one. How would we calculate the starting current in this system? How can we put that a condition? Let's start with that. How can we look at the system? What changes when the rotor is at standstill, to calculate the starting current? Where does that information go in the circuit?
Is it S equals 1?
Exactly, that's S equals to 1. All right. When the rotor is starts, the speed of the rotor is 0, so the slip factor is 1. S becomes 1. We can replace S equals to 1 and solve for the input current to the rotor. So you notice here also that the problem says is a 460 volts, but that's the per phase. That's not the per phase voltage. Per phase voltage is that divided by square root of 3. That's 265. Okay, so one more second. Almost done here. That's the part of the process that you didn't see in control systems. But now you have to patiently wait there as I clean it. All right, here we are. Okay, so that's the circuit. Let's do the first one is the starting current. That's exercise 80A is the current at start. This is hard to read. So how do you do the current at start? At start, remember that the rotor speed is 0, so the slip factor will be 1. Right? S equals to ns minus n divided by ns. This goes to 0, which means that the slip factor is 1. How do we find the starting current? Well, now we need to find the equivalent circuit and calculate the input current I1. How do we do that? Well, this is out of my reach here, but 0.2 divided by S is simply 0.2. Right? So I'll write it here. R2 will be simply 0.2 when S equals to 1. This RC is going to be neglected as the problem states. This goes to 0. And we are left with this part of the circuit and this part of the circuit. How do you calculate the total impedance? Well, the total impedance is going to be this impedance plus the parallel of 30 and this 2, plus the parallel of 30 and those 2. So let's call this 30 ohms here, 30 should be 30J, right? This is a complex impedance. So let's call this Z1. That's this impedance. And let's call this impedance and that impedance, the series of them, let's call that Z2. So Z1 is 30, Z2 is 0.5J plus 0.2. We have this impedance plus that impedance in parallel. So what do you get here? Let's call that the total impedance, which is going to be 0.25 plus 0.5J. These are these two here, plus the parallel of these two impedances. If we call this Z1, if we call that to Z2, what is the parallel of them? What is the parallel of Z1 and Z2? How do you calculate the parallel of an impedance like that? Z1, yeah, go ahead.
Is it 0.5 j omega plus 0.2 in brackets times 30j over the sum of those two terms?
Exactly. Very good. In other words, Z1 times Z2 divided by Z1 plus Z2. All right, so you have 30j times the sum divided by this sum here is simply Z2, right? This two. So Z1, 30, Z2, 0.5 plus 0.2 divided by the sum of them. And the sum of them now becomes 0.2 plus 30 plus 0.5 is 30.5 J. Okay. So again, Z1, Z2, Z1 plus Z2. And this gives the impedance here as 0.25 plus 0.5 J, that's that, right, which is the first part of the circuit, plus 0.49 J plus 0.19. We can add this up, create a vector, and just going to give you the final result here. This is very simple. From electrical circuits, you probably remember this in a phase of 65 degrees ohms. What is the current at start? The current at start is V1 divided by Z, which is 65 divided by 1.08 with an angle of 65 degrees. This is 245, an angle of negative 65 degrees amps. That's the starting current. Okay. As the rotor rotates, what happens to the current? Will the current increase or decrease?
Decrease.
It will decrease. Why will that decrease? Because this 0.2 here, now the slip will decrease. 0.2 divided by a number that is close to 0 will now increase. The impedance here increases, and the current then decreases. Very good. Any questions? No? So let's do, it says steering current. I don't know what a steering current is, but it should be starting current. So let's calculate the starting torque. How do you calculate the starting torque? Then we give the expression here for the torque in general is 1 over the synchronous frequency in radians, synchronous speed in radians per second, V1 squared divided by R1 plus R2 prime over S plus X1 plus X2. I think this is squared. This is a square 2 times R2 prime over S. Okay, so at start, what do we have? When the rotor starts, we know that this is at a slip of 0. Sorry, slip of 1, not 0. Slip of 1 at start. We have everything in this expression except the synchronous frequency. What is the synchronous frequency in radians per second for a 4-pole, 60 hertz? 60 hertz, 4-pole. What is the synchronous speed? One 120 times f divided by 4. That gives 64 1800 RPM. What is the conversion between omega n and ns? Synchronous speed in radians per second, synchronous speed in RPM. Simply multiply this. So simply multiply this by 2 pi over 60, and this gives 188.5 radians per second, which is the speed we need here. All right, we have everything here. Let's calculate it.
Question, sir?
Yep.
When you talked about where we multiply by 1 minus s, well, what condition would that be?
Multiply that by 1 minus s.
Is there a condition where the speed is factored in by the 1 minus s?
No, no.
No.
Oh, I see. Yeah, so that would be the rotor speed with respect to the synchronous speed. That's where the 1 minus s comes in, right? The rotor speed with respect to the synchronous speed. But here we are dealing with the synchronous speed already, so that doesn't apply, right? But if you had to convert between one and the other, if you go from the synchronous to the actual motor speed, you would multiply that by 1 minus s. But that's a different context. So this is that speed. We have V1, the input voltage given here, 256 squared divided by, what is R1? What is R1 here?
$0.25.
0.25, right? This 0.25 there. Yeah, very good. 0.25 plus, what is R2 prime? 0.2 over S. But when the motor starts, S is equal to 1. Right, all that squared plus X1, 0.5 J. Sorry, just 0.5 plus X2, which is also 0.5 squared times R2 prime 0.2 over S. Right? We have everything here, and I just close the parenthesis there. This will give, where I'm gonna find space here. This will give here 162.12 Newton meters. This is for one phase only. We dealt with this equivalent circuit for one phase. What is the total torque? Total torque is 62.12 times 3, which gives 186 Newton meters at start.
Our
Sorry, you said estimate.
shows the voltage as 265 instead. Just a note.
Yes, this is the 250. Oh, did I? 256. Oh, this voltage is the line. It is the line-to-line voltage. The 460 is the three-phase input voltage. This is the phase voltage input. Right? That's phase to phase, and this is phase to neutral.
Sure, it just says 265 on our.
Oh, okay. Yeah, that's more accurate. And let's do 265. Thank you. Okay. All right. So now let's calculate the full load torque when the motor rotates at 1740 RPM. Now the rotor starts to rotate. What changes in all this mess here?
Slip factor.
The slip factor, exactly. The only thing that changes is the slip factor. So I'm going to make some room here for question C. What do we have? The full load slip if now we rotate at 1740 RPM. We can calculate the slip factor, and the slip factor would be 1800 minus 1740 divided by 1800, which is 0.034. Oh, that cannot be. I cannot see this. Actually, let me just get rid of the. There you go. 0.034. What would be the full load current? So if it rotates at this speed, what is the full load current and torque?
Do you just reevaluate with R2 changing?
Exactly. Nothing really changes here, except that this 0.2 is now divided by S over here. Right, it becomes 0.2 divided by S. This S becomes 0.034, and you just reevaluate everything. So I don't think we need to redo that. We can just replace R2 prime over S with 0.2 divided by 0.034, which is 6 ohms. All right, so we go from 0.2 to 6 ohms. What changes? The input current will change. The torque here will also change because this value and this value here are changing. Right. So I'm going to skip that. Just give you the value for the full load current. Full load current would be 43.5 with an angle of negative 19.7 amps. I'll put all the calculations later, but we're really just reevaluating the equation for a different value of R2. And the full load torque will be 162.
Sir, all you did was fill in the S value, right? Make it.
Sorry, I couldn't understand that. Can you repeat it?
For the torque, all you did was replace the S value instead of 1 with 0.034, right?
Yes, that's the only difference. This is for starting. If you do now S equals to 0.034, that's the load torque. Correct.
I'm getting 56.7.
Where are you getting 56? That's
For
1,
the
then you multiply that by 3.
Oh, okay.
That's the total torque, right? You would get 50 and then multiply that by 3. You should get that. Okay, so I just realized that I'm over time again. So I will, if you have other commitments, feel free to leave. I will do the last one, E, the resistance that must be connected in the motor so that in the rotor so that the maximum torque occurs at start. So you have that for the record, because that's very likely to come back at some point in the future. Any questions here?
Yeah, just one clarification. Are we do we have to leave the values? So for example, you see how in I1 you left it with the angle. Can we write it in like the J form or I form?
It depends on what the question asks you. You can do that if you're asking for the magnitude and the angle, then you need to calculate that. But at least the magnitude must be shown. The angle, if required, will be specified, but the magnitude, yes, the magnitude you're expected to calculate. Okay, so let's do just one more for those that are still there. I always go over time. Something with online lectures. All right, so I'll just make some small room here. The last question is the resistance that must be connected in the rotor so that the maximum torque occurs at start. How do you solve that? The resistance that must be connected to the rotor so that the maximum torque occurs at start. Oh, let's look at the slip of maximum torque. The slip of maximum torque, recall that Sm was given by R2 prime divided by square root of R1 squared plus X1 plus X2 squared. If you want the maximum torque to occur at start, what should Sm be?
1.
1, exactly. You can simply equate this to 1. And we need to add the resistance to it. We have to add the resistance to the rotor using one of those configurations that we saw before. So let's add a resistance here, plus R. We have everything in this circuit except for that R. R2 is 0.2 plus R equals to 1 that multiplies the entire square root here. R1 was, how much was R1? 0.25 squared plus 0.5 plus 0.5 squared. So for R equals to 0.9 ohms per phase. And if we add this, then the maximum torque occurs at start. Of course, we don't want this R to be permanently added to the winding because we want to drive a load with the motor later. So this is going to be connected only at the beginning, and then later probably will be removed, will be short-circuited somehow, and then the maximum torque will occur at likely very close to the load speed. Okay, any questions?
I have a question.
Yeah.
Where would this resistor be placed in the circuit when you add it?
1 second. It will be external to the motor. Don't have an example here, but it will be external to the motor in this rings that we added to collect the input, the output voltage here. So remember that the resistance winding will be like that, right? And typically at the rotor side, these are connected, right? But we're going to put them to slip rings like that, and then we can attach another set of resistors to it. It's external to the motor, not permanently, with the mechanism that will allow us to just short circuit them at some point. So the motor goes back to a normal operating mode. Okay, any other questions?
Is the torque the only thing we multiply by 3 when we find its value?
The torque and the power. If you want to know the total power in the system, we need to multiply that by 3 because there are 3 phases. If you want to calculate the total torque, also multiply the torque from one phase, obtained from one phase by 3. Okay, all right. A few questions here. Which of the following does not affect the speed of an induction motor? the supply frequency, the supply voltage, the rotor resistance, the magnetizing inductance, and the stator resistance. Which one does not affect the speed of an induction motor?
Is it the magnetizing inductance?
Correct. That's the magnetizing inductance. Now, everything else affects it. From the equations, we can see them, and you can simply make sense of these statements. If you change the supply frequency, we change the synchronous frequency, and you're changing the speed. Supply voltage as well, because that affects the torque and power delivered to the mechanical part. Same with C and E. Question 2, which of the following statements is true? The starting torque is high, the start slip is low, the maximum torque depends on the rotor resistance, the starting current is higher than the rated current. All statements are false. Which of the following statements is true?
Is it A?
Is that A? Well, the starting torque is not high because of the high reactance of the rotor. So we need some time to develop the current and create a torque. That's why we have this mechanism to shift the point of maximum torque to the beginning. Without that, that strategy, the starting torque is actually low. So it's not A. The starting slip is low. That's also false because the slip at start is 1. The maximum torque depends on the rotor resistance. That's also false. The point where the maximum torque occurs depends on the rotor resistance, but not the magnitude of the maximum torque. So the correct answer is D. The starting current is higher than the rated current. All right, that's the example we just did. When we start the motor, there is a high current. The motor starts to rotate, the current drops. Next question. And this was on the final exam last year. A 6-pole 60 hertz induction rotor normally runs at which of the following speeds?
Is it E?
Is that E? Why would that be E? How was that calculated?
Is it 120F divided by P?
It would be at a 60 hertz. What 6-pole? What is F? Sorry, what is omega n? NS is 120 times
F
times F over P. And how much is this? How much is that? Was this calculation?
So why is it
1800?
divided by 4?
6. Sorry, divided by 6.
1200.
1200. So what is the correct answer?
None of the above.
None of them? Any other guesses?
D.
D. Why is D?
It has to be running at lower.
Exactly. It must be running at a slightly lower speed than the synchronous speed. So the correct answer is D. Very good. Now a tricky one. When the supply voltage of an induction motor falls by 3%, by which percentage does the torque change? When the supply voltage falls by 3%, by which percentage does the torque change?
Is it D? 9%?
Is it D? I see where you're coming from, but is it? The torque depends on the square of the speed of the voltage, so we would assume that is D. So let's say, so the torque depends on V1 squared. If the torque falls by 3%, the voltage would become V1 times 0.97 squared, right? Which would be a factor of 0.94 times V1 squared. So that is 1 minus 0.94, 6%. right? So it would drop by actually 6%. Your reasoning is correct. It would depend on the square of the voltage, but it's actually 6% relative to the original torque. Okay, this is a tricky one. I'm not going to give you this sort of questions on the final. All right. Anything else before we conclude today's lecture? If there are no more questions, then I'll see you again on Thursday. I have extended my office hours on Thursday one more time, so now I added 30 minutes. And if you need to arrange other times, just send me an email. I'll see you on Thursday then. Have a great day.